an unsupervised learning task in machine learning that involves automatically discovering and learning the regularities or patterns in the input data in such a way that the model can be used to generate or output new examples that seem as if they have been drawn from the original data set. So the main task of generative modeling is to generate samples that are similar to the ones in the given data set. So we're trying to mimic, or we're trying to somehow copy the distribution of the training data set. So there are many approaches for generative modeling, and we'll be just seeing how GANs look like. So this is uh, a GAN architecture. So let me just go through the entire explanation of GANs in a nutshell. Um so this will be a brief explanation, and then we'll just look at each of these components in detail. To begin with, what you could see here is we have two networks here in a GAN architecture. Excuse me. So in your GAN model, you have your generator model and your discriminative model. So your generator model is nothing but your generative model that you've just seen, and your discriminative model is nothing but your discriminator is nothing but a discriminative model. So you have two models here, and both of them are neural networks, deep neural networks. And let the generator be denoted by capital G and discriminator be denoted by capital D. So we have two neural networks here. This is a generative model, and discriminator is a discriminative model. All right. So the way it works is we feed a random input vector to your generator model, and the generator model is going to output an image. So this image or this sample is nothing but a generated image. All right. And this real image is basically from the training data set. So it's a sample from the training data set. So once you train your model, once you go on training your model, the generator becomes really good at training, becomes really good at generating real looking fake images. So over time, once you have completely training your generator model, once your complete model is trained, you would see that your generator is able to take an input vector, and it is able to generate images which look like as if they are from the original dataset distribution, original training dataset distribution. So once you have your generated example and your real example, you feed those to your discriminator model, and what your discriminator model does, that it tries to figure out whether the input image is from your generator or whether it's from the training data set. So this is what your discriminator is trying to do. All it's trying to do is it's trying to figure out whether the input image is either a generated image or whether is it a real image. So if it is a real image, it would output a prediction of 1. If it is a fake image, it would output a prediction of 0. So just to summarize, you have two models here, your generator model and your discriminator model. Both of them are deep neural networks. Your generator takes in a random input vector, and it's going to produce a generated image. And this real example is from the training data set. It's a sample from the training data set. And your discriminator, it receives both the images, the generated image and the real image, and it tries to figure out whether the received image is either a real image or a fake image. This is what both the models are doing. Now, the way the training happens is, so once you want to train your model, so what you do is for training your generator, the generator model, so both of these have to be trained separately. Your discriminator and your generator have to be trained separately. For training a generator, just focus on this portion. Just ignore the real examples. We do not feed in the real examples to your generator, to your discriminator. Just ignore the real examples. So for the training purposes, so once I train my generator, the parameters of your discriminator model will be fixed. You do not alter them. And similarly, once I'm training my discriminator, the parameters of my generator will be fixed. They're not altering them. So for the purpose of training my generator, we're not feeding in the real examples. It's just this figure on the left here. So for the training purposes, what we'll do is we'll take a random input vector, feed it to the generator, and the generator is going to output a generated example. And that generated example, we're going to feed it to the discriminator model, and it's going to output a prediction. So since it's a generated example, the prediction is supposed to be 0 because it's a fake image. And so what we do for training the generator, we're actually, we're taking this label, I mean, the label of the generated example as 1. The reason is that, I mean, because that's because we want our generator to be able to produce real looking fake images. We want it to produce data which can be thought of as if it has been obtained from the original data training data distribution. So that is why we label the generated examples as 1 when training the generator model. So we pass the generated example through the discriminator model. So we know that the label y is equal to 1, and we get some prediction here. So what we'll do is we'll be using a loss function. They have used binary cross entropy loss function here to compare the predictions y hat and y. So using that, we use it to modify the weights of the generator model. So this keeps on happening. So in the paper, what they've done is they've trained your discriminator for say five steps, and generator for a single step. For every step, I mean for every iteration of generator, they've trained the discriminator for multiple times. So they've done this because they want the discriminator to be better than the generator, so that the generator model can catch up. Other way of doing this is by altering the learning rate. So they could have increased the learning rate of the discriminator, followed by, I mean, a small learning rate for generator. So that's another possible way. Yeah. So that's how they train the generator model. Now, when it comes to training your discriminator model, so what you do is you're actually taking both the examples, your generated examples and your real examples, right? So in this case, we're feeding in both the examples. So for example, for the first time, when I want to train my discriminator, let me feed, say, the real examples. So when I put in the real examples will be labeled as y is equal to 1. I feed it to the discriminator model, and it's going to give me a prediction. So for real examples, the prediction y hat should be equal to 1. So using binary cross entropy loss function again, I'm going to compare the predictions with the label, and using that I'm going to modify the weights of my discriminator model. Now the same goes with the generated examples. So we have an input vector. The generator is going to produce a generated example. We feed the generated example to your discriminator, and in this case, your label y is going to be 0, not 1. So once you feed in the generated example to your discriminator model, it should predict y hat as 0, but it'll probably say predict say 0.4. So what we do is we basically compare the prediction with the y value using again your BCE loss, and again update the weights of the discriminator. Oops. Yeah. So the difference in training, I mean, the major difference in training that you could see is for training the generator, we're only passing in the generated examples. But for training the discriminator, we are passing in both the generated examples and the real examples. So once the training is complete, your generator will be able to produce real looking fake images, and your discriminator will output a probability of 0.5. The reason is it's going to be confused. It's going to be confused whether the input image is a real image or a fake image. So once your model is totally completed, what we do is we just discard we just throw away the discriminator and we'll be left off with the generator model. So you input a vector, random input vector, and you'll get a generated sample. So that's how GANs work in short. So even though a few parts of it weren't clear, it's okay. We'll be understanding each of these in a lot more detail in just a bit. So yeah. All right, so I'll be taking an example of the MNIST data set for the sake of explanation. So the MNIST data set that we know, it has 60,000 training examples and 10,000 test examples. The shape is 28 by 28 by 1, since they are one channel images. And there are 10 classes here, and all of them are labeled. So yeah, you can see 4, 1, 0, and so on. All right, now let's look at the GAN architecture in detail now. Okay, for now you could just ignore these shaded portions. We'll come to it in just a bit. Okay, so once you look at the GAN architecture, you could see that there are two models as we had discussed earlier. You have your generator model denoted by capital G and your discriminator model denoted by capital D. So your generator model is nothing but a generative model, and your discriminator is nothing but a discriminative model. This is the latent space, and this is the training data set. So this image that you see here is a real image. It's a sample of it's a sample from the training data set, and this here is a generated image. It's a sample. It's a image which is being generated by the generator after we input a random input vector. So this is a generated image, and this is a real image. Excuse me. Okay. So the way it works is the generator tries to generate realistic samples that have never been seen before, and your discriminator tries to tell whether its inputs are real or fake. So the way they work is you take your random noise, you take a random input vector. So I've taken a 64 dimensional vector here for the sake of explanation here. So I'm taking a 64 dimensional noise vector. I feed it to my generator, and so in the output layer, you could see there are 784. We get a 784 dimensional vector. So this is because 28 by 28 is 784. So once you get a 784 dimensional vector, you can easily generate an image. So this is nothing but a deep neural network. So both of these are deep neural networks. You could see we have your z values and your activation functions, which is nothing but g of z. I think they're using the ReLU activation function here for both of them. Okay, so you input a 64 dimensional noise vector and you get an output which is a 784 dimensional vector, which is nothing but a 28 by 28 image. So this is the generated image. So you pass in z and you get g of z. And over here, you have just taken a sample from the training data set. So once you have your generated image and the real image, you pass them to the discriminator. So for example, when I'm passing the generated image through the discriminator, so first of all, it'll be converted into a vector, 28 by 28 by 1, which is 784 dimensional input vector. And using the input vector, it would give me a prediction. So over here, since it's a generated image, the label is going to be y is equal to 0. And so the y prediction here should be close to 0. So this is when you're training the discriminator. So once you pass in the real image, we'll label the input image as y is equal to 1 because these are real images. You pass into the discriminator and it'll give you a prediction. We'll see how the training happens in just a bit. All right. So this is how your model is basically working. So now if you look at this shaded portions, so what you can see here that this actually denotes the distribution. Okay, let me use the pointer. So this actually denotes the distribution of your training data set. and this is the distribution of your latent space. So over a period of couple of iterations, say 10 iterations, 100 iterations, 10,000 iterations, you could see the distribution of the generated samples somehow is able to, after the training, is able to match the distribution of the real examples here. So you could see both the distributions are matching here. So this happens after training. And all the dots that you see here, they're nothing but samples, uh, samples of images. So these are nothing but the training samples. All the dots are training samples, and this shape that you see here is just a distribution, the training data set distribution. So after training the generator for a couple of epochs, so after a couple of iterations, you can see the the distribution, that it is able to mimic the distribution of the training data set. So we are able to mimic the distribution of the training data set, which is here. Secondly, if you look at the probability distribution plots here, so this denotes the probability distribution of your training data set, the original data, and this actually denotes the probability distribution of the noise. Excuse me. So as you increase the number of iterations after you keep training your model, you could see that the distributions are being overlapped now. So both the distributions are overlapping. This is because both the distributions are very much similar to each other. So the black plot basically denotes your probability distribution for your training data, and the green one denotes your probability distribution of your generated data. So as you increase the number of iterations, as you keep training a model, your both the distributions are overlapping, which is a good thing. That is what we want. So once a model is trained, you'll be able to output generated images, real looking fake generated images. Okay. So let's look at the training portion in detail, how we train the